some of these integration rules already. We're kind of exploring and discovering with them in the last section. But now we could compare them to our actual differentiation formulas or derivative rules, right? The derivative of a constant is 0. So the integral of 0 is going to be a constant. The derivative of a constant times x is just going to be the constant. So as expected with the antiderivative, right, or the integral of a constant is just going to be the constant times x. So again, you see them here, how one undoes the other, right? Okay, one rule that I really want you guys to pay attention to is the power rule. When you take the derivative of x to the n, we know that's going to be equal to n times x to the n minus 1. Again, you get the degree and you multiply it as a coefficient and you lower the degree by 1. So for the integral, for the indefinite integral, you're doing the opposite. So instead of getting the degree and subtracting it by 1, we're getting the degree and we're adding 1 to it, right? We're adding 1 to it, and instead of multiplying by n, we're going to be dividing by n plus 1. So that's going to be the main rule here. Make sure that you guys remember this one. And again, the easiest way to remember everything is just kind of like the opposite of or the inverse of the derivatives, right? And you have some trigonometric rules here. Again, just kind of compare them. Make sure you make note of them. And then we have our transcendental functions, right? E to the x, our ln x functions. So you want to make flashcards. You want to remember these. Some of these could be a little bit tricky. So make sure that you guys are making flashcards and practicing them. Just you have to have them memorized. That'll be the fastest way to do well on the test. All right, there's a few tricks I want to go over that will help us take the integral of a function. So if I take the integral of 5e to the t plus 1 over cosine t, the best way to kind of think about it is first of all, you want to take the integral of e to the t, and we already know that's going to be easy. It's just constant, and e to the t is just e to the t. But cosine 1 over cosine squared t is better to express it as secant, using those trigonometric identities, right? Secant squared t. And the reason why we want to do this is because of our trigonometric rules. We see that we could take the integral of secant, it's just tangent, or again, you were kind of thinking to yourself, well, what the derivative of what gives me secant squared? And you should have had that remembered or memorized. But again, that would be one trick here, because now when we take the the integral of 5e to the t, we're just going to get 5e to the t. Just kind of like the derivative, right? Doesn't change anything. And then when we take the integral of secant squared t dt, we're going to get tangent t. And don't forget your c. Okay, the second trick. When you have something like this, a binomial raised to a power, the best thing you could do is actually multiply it out. Okay, so do FOIL method. 3x minus 1 times 3x minus 1. When you multiply that out, you get 9x squared minus 6x plus 1. And now we're going to be taking the integral of these three, right? By the addition rules, we could take the integral for each term. And I'm not going to rewrite it as each individual term. But we have the constant. We could take that out as well, right? We have a constant here. And then the integral of just 1, we know it's x. So our answer is going to be 3x cubed minus 3x squared plus x. And then don't forget your plus c to include all the different functions, all the different functions that meet this integral, right? They're translated up or down. So the trick, one more time, to make this a lot easier for yourself, just multiply them all out and then do the integral of each individual term. Okay, if I have a rational function like this, the best way would be just distribute or, express each numerator term as its own kind of function or as its own term with the x to the fifth or the denominator divided into each one of those individually. Okay, so x squared divided by x to the fifth can be expressed as x to the negative third. And if I do this for all of them, I get with this, I get this function here, and now I could use the power rule for each one, right? So I'm gonna add 1, and then I'm gonna divide by negative 3 plus 1, right? So in this case, and I'm gonna do that for all of them, and then I'm gonna dividing by n plus 1. So when I take this derivative, I'm gonna this integral, I'm gonna get negative 3 plus 1. I'm left with negative 2. And also, I know that this is going to turn into a negative power, right? Negative 2, so it's going to go in the denominator. And that's negative 2. I think that's negative right here. Okay. Same here. That should be a 4. And again, if I look at this power, there's going to be a negative power, so that's why I'm bringing it down to the denominator to make it positive. I'm kind of skipping that step so I don't have to rewrite everything, right? Negative 4 plus 1 is negative 3. To make it positive, bring it down to the denominator. And that's it for that one. Okay, for this trick, it's the same idea, but now we're going to be doing 2 of the previous tricks here where we're going to expand that numerator, and then we want to make sure that we divide the square root of x to each term on the top. So let me just go ahead and do the first one. Right, I expand this out. I get the integral of x squared minus 6x plus 9 divided by the square root of x, or I want to express this as 1/2. Because we're going to subtract it out to each one, right? So when I do this, I end up getting x squared minus 1/2 or 1.5, right? But we're not used to expressing them in terms of decimals. So it'll be 3/2. Keep everything as a fraction. This is x minus x is going to give us half a power. And since this term doesn't have an x, it's just going to be negative 9x to the negative 1/2 because we are bringing it to the numerator. Okay. Now when I take the integral for this, again, just add a 1. Right. We're going to add a 1, and then we're going to add this to the denominator. So this would be x, add 2 over 2, right? That makes it 5/2. And again, when I add this to the denominator, is going to be 5/2, or the opposite is going to be 2/5. Okay, the reciprocal. Because we don't want to have a fraction in the denominator, so this is the easiest way to do it. Same here. Add a 1. That would make it 3/2. X to the 3/2. And again, we're going to be dividing by 3/2 or multiplying by 2/3. Okay, but we already have a 6. Give me a second. Let me make some room here. So we already have a 6, but we're multiplying by 3/2 or 2/3. And we could simplify that out in a little bit. And again, we have 9. We're going to add 1, right? Or 2/2, which gives us x to the 1/2. And we're going to divide by 1/2 or multiply by 2. And kind of ran out of space here, but I'll just put the little 2 there. Okay, simplify it all out. The 6, we could take out that factor. Minus 4x 3/2 minus 18x to the 1/2 plus c. Make sure you don't forget that c.